That's a segmentation fault means that you have a bug, which is hardly surprising in your first go at this sort of thing. So we'll need, obviously, to look at the, oops, help if I actually, so if you're getting a segmentation fault, that implies that there's a problem with the memory stuff. So let's just have a little look at this. So for the, first of all, we need to think about how are we going to store our data? So up above, we said that we don't need to support resizing of the matrix, and we want it to not be copyable, and we want to have copying done by an explicit copy function or duplicate function, sorry. So thinking about that implies that the unique pointer is quite a close match to this. So I'm just going to go ahead and use a unique pointer. And again, I apologize for introducing templates earlier than I had planned. So let's maybe, no, I need to leave it in because otherwise I have to change all the tests. But let's imagine when you see T, just read double or something. And because of quirks of the thing, we have to specify this is an array of T's. An alternative could be to use a std vectors of T. Let's do that. Let's do that for something different. Okay, because this the data does uniquely own its data, and this means that the copying might be a bit easier because the vector can copy itself. So in my solution, I've done it with unique pointer, but let's do it here with vector instead. Okay, so since Mohammed's having problems and used unique pointer, I'll use that too. So let's use a unique pointer of T array to an array of T's. So what do we need to do? So for this one, that's fine. The default constructor of unique pointer, if we were to go look it up, would show us that it constructs a valid object. So if we look at the constructors, and see here that the no argument default constructor here, it's number 1. So let's go and look it up. And it constructs a unique pointer that owns nothing. That is exactly what we want here. So perfect. So we can just delete that. And then we want this one that allocates some memory. So we'll check it's a power of 2 because that's required. And now let's see, what did I call the members? So it's underscore rank and underscore data. So let's initialize the rank from R and data. Okay, so we need to initialize our unique pointer. So we could use make unique, or we can just directly new it ourselves. So let's just directly new it ourselves. It's a bit easier. So we need a new T, and we need R times R of them, because it's a square matrix. Mohammed, shout out if there's something that you did differently that shows where your bug is. So we've allocated our data here. But here we're saying that we're not going to allow copying just through the language by copy construction or copy assignment with an equals sign. Let's suppose that we really care about performance and we want to avoid doing it by mistake. So we want to allow moving, and so we need to think carefully about whether the default one is allowed. Okay, I'll answer Killian first because that's a quick one. So the sort of the after the colon, the initialization list thing is preferred because it happens before the code starts running. So all you can do in that is initialize things, and it just shows a clearer separation between what's going on here. So one of the things that you can do is you can have constant data members and reference data members. Now, this is generally not considered a good idea to have those, but you can do it, and that is the only place that you can initialize them. But it's certainly not required. It's just idiomatic, really, to try and do that, just because it shows more clearly what's going on. And basically, if there's anything in your body of the constructor, that's kind of special code in some sense. Does that make some sense? Yes, it is probably more confusing. I totally agree. You know, it's more syntax, it's more stuff to remember. But for better or for worse, this is the more idiomatic thing in the you know, the wider programming community. So you know, this is not a gentle introduction. I'm sorry. This is what it is type introduction to the language. Just because of the brevity of the course, there's no alternative really. So Mohammed is doing some things. So, okay, he's doing his test. So I'm just going to copy that into my editor so I can see what's happening a bit better. Oh, so you've got some tries and catches. So it's not entirely wrong. So you're checking the condition, and if the condition is the error one, you're throwing an error. Your problem then is that immediately after you've thrown your exception, you catch it, and you're printing an error message, and then you're going ahead and making the data allocation. So you have printed an error message, but not stopped the program execution. So you have produced an error message, but then just carried on regardless. So if this goes ahead, then I mean, I totally appreciate that throwing an exception in your constructor, if there's an error condition, is a good thing to do, but you're throwing it, catching it, printing a useful error message, but then ignoring it as far as the program is concerned. Why would you want to return 1? I don't understand. I mean, well, asserting is what I'm doing, which stops the program. It would be nicer to have printed an error message first, but this is really just checking things, and the assertion will print an error message for you. It's not a stupid question, it's a perfectly good question, but it's irrelevant because as soon as the assert fails, the program is killed. The operating system will just kill it for you. So there's no quicker way to exit than that. And the thing to remember is that, so I've been trying to avoid exceptions in the course to a certain extent, but the nice thing about exceptions is if you throw one and it starts propagating out of this function, every time it propagates out of one of these blocks with the curly braces, not just try-catch blocks and such, every time you leave a curly brace, the variables inside that will be destructed. And so here, when we leave the constructor via exception, the data members will be destructed in reverse order. So data will get destructed and rank will get destructed, but rank's just an integer, so that's a no operation. But because data is a unique putter in this case, it will have its memory deleted and there will be no leak. It will be an unnecessary memory allocation and free, but exceptions have to be, in C++, exceptions incur a very large runtime cost. And so you should only throw an exception if it's an exceptional situation. In the code that I have written for HPC type things, the only thing I do with an exception is let it propagate and print a nice error message at the end. So my main function in the at the top of the program has something like try, do the simulation with these arguments, catch, print the error message, catch the exception, print its error message, basically doing std e what, and then it exits with 1, because the runtime cost of an exception is just too high to pay inside inner loops. Okay, so I would say this code is bad. I would not try and catch an exception like that. Okay, because this try catch thing is not actually having its desired effect of stopping the simulation, the program execution. Okay, so copying has been marked as delete, okay, and then moving is allowed. So we need to think about whether the default implementation of move is going to be okay. So for moving an integer, that's fine. That is just a copy. That's not a problem. We need to think about the unique putter. So if we look at the documentation again, we can see, where does it explain? It's a smart pointer that owns and manages another object, blah, 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 when it goes out of scope. Okay, it can be movable, yes. So you can see this, for example, looking in the constructors, you can see that the move constructor here, number 6 or 5, sorry, looking at the wrong one. Where's 5? It constructs a unique pointer by transferring ownership from the other one, u, to this, and it stores the null putter in u, the other one. So that is exactly what we need, so we can rely on the defaults. So because in this type we have defined a destructor, deleted the copy constructor, and defaulted the moving constructor, we hit the rule of 5. Okay, so because we've got 1, we've got to have all of them. I'll answer you in a second, Eric. So if we've got one, we have to have them all. So the question is, can we use the rule of zero to not bother with any of them? So to do that, we need to look at what we've chosen as our data members. So the integer rank is uninteresting. That's not a problem. The data pointer needs to be thought about more carefully. So unique putter does have the same semantics as what we've got. So we can, in fact, if we use unique putter, rely on this, and we can just remove all of these things, and it will do what we want as the right thing. However, if you choose to use a vector here, because a stud vector is copyable, okay, that means that we need to explicitly add the deletions here, which means that we should also provide the other ones. So using a stud vector is not a bad choice. It is a reasonable choice that has a small additional cost to you, the programmer. At runtime, it will have no additional cost, just to emphasize. Although technically using a stud vector will make your class, the size of your class, fractionally bigger, because stud vector needs to hold a little bit more information, because it doesn't just hold a pointer, it holds the size, it holds a pointer, the size, and what its current capacity is. So it has to hold three things versus just one that the unique putter will hold. So it does carry a fractional cost, but it's not a bad choice. I just want to make clear. Okay, so we need to provide some other things. So let's do element access quickly. So we're saying, give me a access to the element at ij. So what do we need for that? We need to think about using some of these helper functions that are provided. So we need to know what the index is. Let's just call it Z. We'll do the necessary bit messing around for that, and then return the zth. That's a hard thing to say. The zth element of data. For it's this bits stuff here. So like I said, this computes the 2D code for a given pair of things. Then we have this version, which gives you read-write access to a member, and this is in fact exactly the same. So you can do a copy and paste, or you can do a little naughty trick. In C++ 23, it looks like this is going to be fixed, but it's not guaranteed yet. This is just something that's happening. So but also providing a way for our users to get in and see the raw data array here as well. So that is just a member of data. So because we're using unique putter, we want to call get on that, which is the member function of unique putter that will expose the underlying pointer. And the same here. If you were to use a vector, then it would be the vector dot data. So this is exposing a similar thing to that. Try and compile that. What have I done wrong here? Oh, it doesn't name a type, of course. I didn't include memory. That is a good point, compiler. Okay, so we now have a passing test. I did not actually provide an implementation for this. So there's an easy way, which we'll talk about later today, and there's the slow way. So I am just going to do the so Mohammed, that is unfortunately not going to help you at all, because what you've just done is you've taken your data and you've given it to someone else, and you've left your size at whatever the rank was before and given away your data to someone else. So this is unfortunately wrong, and this might be causing your segmentation fault if this is used. Does that make sense? You understand why that will fail? Great. Yeah, so I'll talk about what this is doing a bit later, but that's just much quicker to type. Oh no, I can't do that until I've done the begin and end to make the iterator thing work. Sorry. Getting ahead of myself. So shall I talk about the other part of this as well now, or are people feeling fairly happy with this? If you just raise your hand or say something, I'll do the second part. Okay, right, great. Okay, great. Okay, that's fine. So there we go. For this one, I've put in a, oh, hold on. That looks like that's the wrong thing. So I've put in some stuff to implement this, a potential solution to the first part that works. And now we need to think about this one. So what we have to do first is we have to declare the other one. So just ignore the template stuff I've highlighted there and just imagine it's just says class matrix iterator. And this is saying to the compiler, there is a class called matrix iterator. Okay, so that's all that this is doing. It's saying that the name matrix iterator will represent a class. So this is going to allow us to use it somewhat here. And we're saying, we're thinking about that here. So we've got exactly as before, the destructors, our duplicate, rank, size, element access, and so on. And now here we come down to the to-dos, where we have to implement functions that are going to get our iterators for us to the first element for begin and the one just past the last for the matrix. So we need to think about how we're going to implement our iterator. So here we're doing this stuff around inheriting from this iterator thing. Now, unfortunately, the language is in a state of flux around what's happening to this, because in 17, the language standard is saying, don't use this anymore. But there's an awful lot of code that's been written in the before 17 that is going to use this. So I've left this code like this there, using this thing. And this is basically a way to tell all the standard library algorithm the things you need to be a bidirectional iterator, which means an iterator that can go forwards through your data as well as backwards through it the other way. It's fairly easy to change this to what's called a random access iterator, where you can jump from any point to any point with a constant cost. It's just that you end up having to implement a whole bunch of extra functions for it, and to keep things relatively simple, I have decided not to do that. So we need to think, first of all, what data is this going to hold on to? So we need to think about how we're going to point in to the matrix's actual data. So what might that be? We need to know a couple of things. So we need to have the most basic thing that we need is we need to have a pointer, and let's suppose this is a raw pointer to the current position. So let's call it that. And we might also want to know which what do you call it, array we belong to. For example, if we want to be able to get the x and the y coordinates of the current element. So we could hold that pointer, or we could perhaps, because we don't actually need to know which matrix we belong to. We just need to know where does its data start. So let's have that also of the same type, start and pointer. And in the case where we're being default constructed, we probably want these to be null to make sure that it's not going to accidentally mess around with something. So the default constructor is fine. It can be default. And because we're going to go and define some other constructors, I need to explicitly default this. So to do the x and y parts, that's just going to be something from the bits. So we need the decode function. So we pass in our z index, the current index, and then we'll get out x and y from that. So we need to know what z is. And I think I'm going to have to explicitly specify the type, yes, because that needs to be type. So we need to know what our z is, and this is why I put the start pointer as well as the other one is. So if we just take the offset of our current position from the start, that will tell us what z is. And then we can call, and it's int 32t xy. Then we can call decode. It is decode or is it encode? I'm getting myself back to front. Decode XY. Okay, and then we have the same here. Returning Y. Okay. So we need to think about equality comparison because we need to know when we're doing our loop, we need to say, is the current iterator equal to the end yet or not? Is it still not equal to the end? So for this one, we need to think about here. So it's the putters. A putter equals B putter is sufficient. If they are pointing at the same element, the iterators are equivalent. So we can just return that. And then for the not equal one, we're just using our other function. We're just saying it's the opposite of that. So to get an element, this is again relatively straightforward. We have a putter to our data. We are just going to return that dereferenced. Okay, so to go to the next one, again, this is quite simple. We take our putter and we plus it. But then we need to return the current instance. So we need to return this. So unfortunately, for historical reasons, this magic keyword this in C++ is always a pointer to the current instance rather than a reference. So yeah, that is basically because C++ did not have references when the classes were added. Okay, so Eric's asking, don't we need to take the size of t into account? No, because the language does that for you. If you have a pointer to some type and you add 1 to it, that will go to the next one. It won't move 1 byte forwards, well, unless of course you're dealing with characters or something that are 1 byte wide. So this is something inherited from C as well. So if you take a C pointer to a double and you plus on it, that will move 8 bytes forwards in memory. Yes, thank you. Good bug spot, Andrew. Okay. And because we're a bidirectional iterator that can go either way, we need to provide the backwards one. Okay, so we need to declare and define some appropriate constructors to construct these iterators. Okay. So we want to say the matrix. What information does this iterator need to be constructed? It needs to define the 2 pointers. So we need a start and a value and where we are. Let's actually spell them out, it'll be easier. And, well, this is quite straightforward. We just set them. Right. So we've set our 2 putters. Let's see. I think I've done most of the things. We'll find out when I try and run this. So where's my begin and end? Here we go. So begin, I need to return an iterator. A matrix iterator of t Again, apologies for that. And we need to, first of all, we need to put our start. So that is just data, find above. And that's the start one. And the current value is just also data. And for the end, well, the start is the same, but the end is different. So we need to take our the start of the data, and we need to move to the element just past the end. So that means we need to add r squared to that. For any Python-only people, just a reminder that C and C++ do not support exponentiation as an operator, unfortunately. So for the const iterator one, someone asked a question about that. We need to return a matrix iterator for a constant t, for t that's constant, and the same for the end. Oh, I'm still in the wrong one. Okay, so it's not R, it's rank or underscore rank? Underscore rank, yes. Thank you. And I've missed a semicolon on something on line 161. Indeed. Okay, so it did something. Okay, so I've done what was required there. Okay, so perhaps it makes sense for me to do the template thing, and then if there are any further questions about this, I'll answer them then when we know a little bit more about templates. Are there any objections to that? Eric, I notice you have your hand up. Is there a question? No. Okay, great. I'll do that then, and then very happy, of course, to answer any questions about stuff. No worries. Okay, so there've been lots of hints at this already. So we've had stood vectors, shared pointers, unique pointers, that exercise that I should have removed the templatiness from. So let's motivate and stuff for all this. Yes, I shall push a branch to the repository with all my solutions in it at the end of the course. Great. Okay, so was it the very first lecture we had some functions for adding numbers? So we'll think about that as a little example, because what templates are is they're not a way of writing a program. They're writing a program that is gonna then produce code. It's a program to write a program. So it's one level higher of abstraction to deal with, which is obviously a little more complex, but it does allow a great deal of power. And because this program is written for you, you have less to write, and it is done by the compiler. So hopefully, fingers crossed, unless there's a compiler bug, there's no errors, unless your template has errors, of course. And you can do stuff with templates at compile time that does not incur a runtime overhead. So this is good for performance. So going back to the sum thing, so we've got adding integers, we've got adding doubles, but we can start thinking about doing this for more types. What do we want? Floats, unsigns, complex numbers, and so on. This is going to be a lot of hassle to get this right every time, especially if you have multiple other arithmetic operations, and it's a maintenance burden. So let's write a template to do this. So here's the syntax. You have to use the magic word template to say to the compiler, this is a template. And then inside the angle brackets, the less than, greater than pair, you list the parameters of the template. So just like for a function, you list the parameters. You were saying this one takes an integer a and integer b. So it's giving names to these local variables. These things are the template parameters. And you can say T is a type or a type name. You can also say class here instead of type name. They are exactly synonymous inside the template parameter list, type name and class. I have no strong feelings about which one is better. Personally, I prefer to use type name everywhere. Other people have different opinions. It does not really matter. Again, consistency within an application and or a code base is much better than any particular thing. So you have introduced a template with a single parameter, which I'm calling T here, T being the sort of canonical name of a type, if you're not caring too much about what properties it has. And then I'm saying this is a function, okay, because I'm declaring a function that uses this type name T. And it's called sum. It accepts two T parameters called A and B, and it returns a T as its answer. And then inside the braces, just as with a normal function definition, I give the body, which is just A plus B. So these two types have to support operator addition. So when you actually come to use this later on in your program, you can instantiate this template on a particular type by explicitly saying what the types are and putting them inside the angle brackets. So here I'm saying sum on an unsigned. Okay, so this is going to go in, and the compiler will say, okay, sum is a template with one parameter. That parameter is now unsigned. So whenever in the body of the template it sees T, it will substitute in unsigned for us and then compile that code. Christoph asks, how is this better than defining an add member function on the custom types directly? Okay, so there are several things that would not be great about that. First of all, you can't do that for the built-in types. And obviously with addition, that's irrelevant because you would never do it for addition anyway. Okay, this is a somewhat contrived example doing this addition with addition. Okay, but it's a simple example, so let's not worry too much about that. Second, if you want to, instead of using a template free function, a free function that's a template, you have to control the source code of those members of those types. So you would have to be able to modify those, and that may not be something that you can do. They might be part of the standard library that you want to work on types. The types you work on, they might belong to some library that you don't control, that you're just using. And it could well be an open source library that you could just go in and modify anyway, but that's a whole lot of hassle, and do you really want to be carrying around a patched version of some big complicated library? I think that's a thing you'd only want to do if you really had to. And Killian asks a good question about auto there. If you're lucky enough to be using C++ 20, yes, you can do that. basically in C++20, the language has adopted templates more deeply. So you can say something like that will be transformed into a template function of 2 parameters, which will be separately A and B. So it would be that. Yeah. If you are in 17 but not 20, you can put auto as your return type of the template, and the compiler will basically look through the entire function definition and figure out what type you're returning. So if you're in 17, you could write this as auto sum TATB. But, you know, do you want to? It is hiding more information from your user than perhaps you want to. Because here we're saying that the 2 types have to be the same, and this is also going to return the same thing. Whereas with the auto sum, auto A, auto B, all 3 types are variable. Okay, so we talked about what happens when you instantiate it explicitly. When you instantiate it, the compiler substitutes the template parameters for the ones it's got, and then it compiles the code. Okay. So we can do this for unsigned integers and floats. So we've now got these things. But you can also let the compiler deduce the template parameters for you. And this is called implicit template instantiation. And there are a few little wrinkles about this that we'll talk about in a minute. But basically, the compiler will do similarly to what it does during overload resolution. It will say, I know what the types of this function are, and then it will look for any functions with that name. Marcelo is asking, can you have different types in the template? Yes, so you can have a template with 2 parameters. So you could have something like, exactly as you're saying, type name T1, type name T2. So let's suppose we're in C++ land, C++17 land. Where we're just going to let the compiler figure out the return value for us. Okay, you can have an arbitrary number of template parameters. You know, I think it's one of these things where the language specification says it's up to the compiler to choose how many parameters it will support. In principle, any number. But if you're getting more than about 5, it's going to get very unpleasant. So Marcelo's, Killian's asking, can you pass a template into a template? Yes, this is called a template parameter. There are uses where you might want to do this. Do you really want to do this? It's getting a bit complicated. I mean, I have written a handful of template functions. So Marcel is asking about auto. I can simply use auto and let the compiler match the signature. Yes, you can. You can do that sometimes, but do you want to do that? The compiler can, you're getting a bit Python-esque if you're doing that. If you're saying everything is generic and it can accept anything, it's basically starting to be a bit like Python's dynamic typing, except it's done at compile time. So it's like duck typing. If it's got an operator plus and an operator minus, then it's a number, which might work, but maybe it won't. And it's not really, it's getting a bit advanced for this course, but there's a thing called concepts, which has been introduced with C++20 that lets you tame this problem. So you can say, okay, I'm only going to accept types that have some properties. And you can give those properties a name, and you can express to the compiler a way to check for these. But then the syntax of using them is much nicer. Okay, where have we gone? Okay, so you can let the compiler do the deduction for you. So you can pass it two unsigns, and it will deduce correctly that t should be an unsigned integer, and it will return one for you. And the same for the floats. The problem arises if A and B have different types here, and so on. So we did template functions in 4 slides or whatever it was. Let's talk about template classes. And this is basically a template that when you instantiate, it will produce a class. So let's just think about the myArray thing container, simple container that we had before. And let's promote it to, instead of holding only doubles, it can hold any type T. Okay? So again, we have the template keyword that introduces this as a template. And inside the parameter list, we have a single parameter. Okay, here I'm using class, just to emphasize that this is allowable. We're giving it the name T again. And then immediately following the template parameters, you have your class body. So we're saying it's a class, it's called myArray, and here comes the definition. So we've got our members first of all, and as before, we have the size being just an integer. And now we have the data thing. So instead of it being a pointer to a double, it's a pointer to a T. And that's fine. When you instantiate it, the compiler will substitute T for whatever type is provided, whether it's a double, whether it's an int, whether it's some custom type. And then we have the member functions. We've got our default constructor, our value, our sized constructor. We need to think about copy and move now, because is our type T going to be copyable or movable? Then you've got things, the destructor is before the size and so on. And then another difference is our member access. So again, instead of returning a reference to a T, a double, we're returning a reference to a T, and so on. So one thing to note is you can treat the template parameter like any other basic type. You can add qualifiers to it. You can qualify it with an ampersand and so on. So one thing that you can do, and especially when you start doing more templates, is it's very useful to be able to give a new name for some particular type. And the way that the language supports this is called a using declaration. So I can introduce an alias for something type, and I can call it my very important type, whatever. You know, it's not that uncommon for scientific numerical codes to have something like using real type equals int or float, and this is a thing that you choose at compile time, and this will compile your entire application using single or double precision floating point values, depending on what you're trying to do. And we can also have more useful things. So for example, we might have a map from strings to vectors of some hard to and long to type name, and then we want to know what is the iterator type it is. So you could just have using iter equals all that jazz. And this, using these aliases is super, super common if you're writing, for example, a template class, because sometimes it can be very hard to figure out the type parameters it was instantiated with in another bit of code that might be useful. So, for example, going back to the myArray, you might want to say that the value type is a T, and you might want to make this visible to the users of your class under a nice clear name. And in particular, this choice of the name value underscore type is the one that is made ubiquitously in the standard container library. So that's why I've made this one here. And the same for reference and const reference and so on. And then you can use this in your template definition to hopefully more clearly express to any readers what's going on. So I'm saying this one on the const variant returns a const reference, and this mutable one returns a mutable reference. Okay. So I mentioned that templates aren't code. They are a recipe for making code. So this means that the definition of your templates has to be available to the compiler when it's translating a particular source file. So this typically means that templates get put into header files. So you can do this in a couple of ways. You can define, for example, the member functions inline in your template definition, in the template class definition. Or you can put them at the end of the header file, just in the same way you might put a normal class's member function declarations outside the class definition. And in that case, you would just commonly put them in the CPP file corresponding. But because these templates have to have all the details available when they're used, they need to be put in the header file, or equivalently in another file, often called something like .txx, that gets included at the end of the header file. So the syntax for this is pretty similar to what you might expect. You've got to note that you have to say that this definition is a template. So it's template, whatever the parameters are. Then you say it's working on myArray instantiated on a T, and it's the constructor which takes one unsigned, and then you give that before. So it's, it's a slightly uglier syntax in the second form, but on the other hand, it makes the class definition much cleaner and easier to read if it's only got the member function declarations visible. So, there are pros and cons to doing this. Rule of thumb is like maybe if the function body is more than 3 or 4 lines, you want to be putting it, doing an out-of-line definition of it. Okay, so another thing I said yesterday or the day before was that everything that you use in a C++ program has to be defined exactly once in the program. And this has 2 exceptions. First is for templates, because of exactly this behavior had before. And the other exception is for a function that has been marked as inline. Now, I haven't mentioned inline functions, but this is what they are. This means that this is a function whose definition can be stuck in a header file, just like a template's definition has to be stuck in a header file, and that these are allowed to be repeated many times in many separate compilations, or what are called translation units. And then when you come to link your program together, where you take the many object files that make it up and link them together to produce an executable, what the linker does is it picks arbitrarily one of these definitions to use in the final program. And so you need to make very sure that all of these are identical. So you need to make sure that you've put them in a header file and that your compilation is up to date, so your makefile understands that a change to a header file in your program means recompile any source file that depends upon it, even indirectly. Okay, so this is a strong argument for using a build system that understands this. If you're going to write your makefiles by hand, this can be non-trivial. What is the use of allowing what? Sorry, Christoph. It is basically to support templates, because if you want to use a standard vector of integers in multiple source files, you have to have the definition available in every source file, because they are not code, they are a recipe for making code. And inherited from C, but slightly more formalized, is this thing called the one definition rule that says that any bit of code has to have exactly one definition, because otherwise how can the compiler pick from them? But the necessity of having the definition of the template available in every translation unit means that there has to be this special casing of templates, and the linker needs to know about it so it can go, okay, I pick that one, or whichever one it does. And so it is up to you, the programmer, to make sure that every definition is the same. And this really comes down to using a build system that supports it. So if you're writing your makefile yourself, you need to take a lot of care, which is why you don't write your makefile yourself unless you really, really have to. So inline is just a special keyword that says you can do this. And this means that the full definition of your function is available to the compiler when it translates your source code. And this is going to help the compiler to do function inlining, which is where it says, okay, you're calling a function inside the middle of your fast loop. Maybe I should take that code, replace the function call syntax with the actual code, and then do my optimization things, because maybe I can make that faster. And so it can do things like hoist some operations outside the loop, and it can just avoid the jump in the program to a different place in the program, which does incur a small cost at runtime. And if you're doing that inside a loop, that can cost you. So it's basically a function marked inline is not guaranteed to be inline. It just makes it a lot easier for the compiler to inline it. So you cannot use a function from another file in a template. Yes, you can, as long as the declaration is available. So you can call any old function you like from within a template, as long as the declaration of the function is visible to the template. There are very few restrictions on the code you can put in a template. Okay, Eric's asking about link time optimization, which does indeed do the same thing, yes. But not everyone has a compiler that supports LTO. Not everyone can do that. If you've got a large program, doing LTO can take a very long time, so you might only do that for, you're like, I'm sure this is going to work now, I've tested it, I'm about to start doing a lot of simulations, okay, I'll do the slow compile now. And LTO doesn't guarantee to do this. You know, it's a simpler way of doing the same thing. Some build systems also really don't get on with LTO or whole program optimization, whatever your compiler calls it. I mean, there's nothing wrong with LTO. I think it's great for performance, but sometimes a bit of a bother to get it working. Mohammed's asking, can I have templated methods if the class itself is not templated? Good question. Yes, you can. You just need to make sure that the template function is visible. It has a definition in the class definition, or you know, immediately following it, because any users of it are going to need to know what that is. Unless, of course, it's private, in which case you can put the template definition in the implementation. That might be a thing that you could do. Okay, talked about templates and type deduction. So we had this, and without specifying explicitly what t was, if I've got two integers x and y, and I'm calling sum on that, the compiler will do this template argument deduction thing. And this means that it looks at the types of the expressions, because this doesn't have to be x here. This could be 1 plus 2 or something. That are passed as arguments to the function. And then it tries to choose the t such that the type of the argument and the expected type of the parameter match. And it's important to note here that the template parameter t and the type of the function arguments might be different, but somehow related to each other. In the sort of formal terms of the language, you would say that the parameter would be a dependent type. It's something that depends on a template parameter. So we've just got a plain function that takes a plain old value t here. And here I'm saying that x is a reference to a t. X is a constant reference to a t. X is a forwarding reference to a t. Notice I'm saying forwarding reference here, not a R value reference. And here I'm saying x is a vector of t's. And I'll come back really shortly on that long. And if you just call any of these functions on a value, these extra annotations on the type of the parameter are going to affect what the deduced argument type t is. I'm sorry, I didn't have an example. So if I have a vector of t's as my parameter, and I call each of these functions with just that vector of t's, vector of integers, say. So in this case, t will be a stud vector of int. And in this case, t will again be a stud vector of ints, because if it's a mutable value and I pass it to a function that's expecting a reference, it's going to be allowing modification of this. Again, if I use the same example, calling it on this one, I'm going to get t being a stud vector of t. Then in this case, what's going to happen? So this is the difference. This is a forwarding reference. And what it's going to do is it's going to take the type t to again be a vector of t, a vector of integers, but it will allow modification. This would equally well accept an R value as well, and it would preserve through the function interface what whether it's forwarding, whether it's an R value reference or an ordinary reference. Then this case here, t will obviously just be integer, because that is the value of t that when substituted in here gives something that could be a vector of ints, and in this case it will copy into the parameter from the past thing. So I'm going to come back to the type deduction thing, but it's also pretty important to mention another thing. You can give a template what's called a non-type template parameter. Yes, again, I apologize for the language, but that's just what it's called. We've had one of these already in our stud array thing, where you have to specify both what the type of the element is and how many there are. And so things that you can use as these non-type template parameters are basically integers, pointers, and enums, unless you've moved on to C++ 20, when you can have things like floating point types and any type, which is what's called a literal type. You just need to look this up if you are interested in doing this. So you could have things like a statically sized vector, where the parameter is just n. You could have a matrix with a number of rows and columns. And then you can start doing slightly more complex things. You could say, OK, I want to have a multiplication operator that accepts a matrix of arbitrary size and a vector of a compatible size. So notice that I have two parameters here, the number of rows and columns. Matrix has whatever size, but then the vector argument has to have a compatible size to match the number of columns in your vector, sorry, in your matrix. And then the result vector that you're going to get is going to have the correct number of rows, for an arbitrary rectangular matrix acting on a compatible size vector. And one of the nice things about this is if you were to, you go all the way down, all in on doing this, you get everything checked is compatible sizes at compile time, which is nice. And you'll get an error message at compile time if something goes wrong. And did I mention that the size of your answer is correctly deduced? So all the full rules for this are fairly complex, but you can usually ignore them and think about just a few things, which are, first of all, whether you want to copy the argument to your template function or not. And if you don't want to copy, add a reference. If you do want to copy, leave it undecorated. Then you need to think about if you could handle a constant argument. And if you can, add a const qualifier to that. If you can't, if you need to modify it in some way, don't add it, of course. And if you want exactly the type of the expression that was passed in, add this double ampersand, which is called a forwarding reference in this context. And I promised this earlier, the auto keyword has exactly the same rules as template argument deduction for you. So that is why these rules that we have here are pretty similar to the ones introducing auto earlier. Okay, right. So having looked at that, are there any questions about the, sorry, what am I doing? The matrix exercise or not? Okay, if not, let's stop for a bit. There is a short exercise about templates. Where's that gone? Oh no, there's not. What did I do with that? Yeah, so let's come back at 11:15 and we'll talk about algorithms. Great. Yeah, I'll see you all in at 11:15 if that's all right.